Welcome back, everyone, and now hopefully with a better voice. So we had in the previous video the topic of local PCA, and here you see still the last slide for summary and discussion about the local PCA technique. So this is the first, so to speak, answer that we have to our problem, like the metabolite data set with disease 1, disease 2, and disease 3, and how we can do justice to this data set by finding the clusters that reside in arbitrarily oriented subspaces individually. But we need some kind of like overview. So what I try to convey or hope to convey in these videos is like a zoom in, like a zoom in local PCA and a zoom out. So we are looking close and then like in Google Maps, pinch to zoom out to have the bigger picture again. And we ask at this stage, where are we now? So in the topic of high dimensional clustering, we have this axis parallel subspace clustering, to which we have this subspace clustering, which permits, as if you recall the slides from Professor Krüger, which permits overlapping subspaces, which permits overlaps in general, and projected clustering where one object is exactly assigned to one and only one subspace. Then we have this pattern base, which also Professor Krüger introduced you in the last week's session. And we are here in this field of arbitrary-oriented subspace clustering. And now if we zoom in into this field of subspace cluster, arbitrary-oriented subspace clustering, we recognize, wow, there is quite a lot behind it. So the first like division or the first two categories that we can introduce is like multiple subspace optimized clustering. Multiple subspaces, as the name suggests, probably that each cluster gets its own subspace. And on the other hand, there is also this single subspace optimized clustering. Now you may say rightfully, wait a second, a single subspace for all of the clusters, but isn't that actually PCA? The answer is on a very high level, yes, because you try to figure out in single subspace optimized clustering a single subspace in which you can then find the clusters when the objects are projected to that subspace. You try to figure on that subspace then the interesting clusters. Nevertheless, these works that you see here, like LDA, k-means, sub-k-means, FOSS-CLUE, and so on, they have some real smart approaches which go beyond the idea of PCA itself, of only applying PCA. So for instance, what something like FOSS-CLUE does, it tries to find out this rotation or this subspace in such a way that it maximizes the separability. So it's that the clusters that are detected are as good as possible separable from each other. So it enforces multimodal expression of the data in this cluster subspace, while on this orthogonal, on the so-called noise subspace, it tries to enforce a unimodality. So it says noise has to be expressed by one distribution, while clusters have to be expressed by several distributions that are well separable, just that you get a high-level idea. And for that, they use techniques like so-called Gibbons rotation. And nevertheless, these single subspace optimized clusterings, they still have the potential limitation that also PCA has. So this is not an exception to the rule. If you have something like a parabola, if you know there may be something in your data set which is inherently nonlinear, then a single subspace, a single linear subspace, all of the three are detecting linear subspaces, do not properly encode or represent the original data. So in such cases, you wish to go for multiple subspace optimized clustering. There we have local PCA, as we have discussed before. Then there's another technique known as locally linear embedding. It is interesting that, for instance, local PCA has been used originally in 1993 for nonlinear embedding, so to speak. And this locally linear embedding is a method from the so-called manifold learning domain or research field. So the idea in manifold learning is to, if you have, for instance, an S-curve in your data, to learn this S shape. And this S shape is, for instance, here learned with local linear embedding by learning it piecewise in piecewise linear patches. So this is the idea behind local linear embedding, roughly speaking. It is interesting here, or I emphasize this because you see the whole topic of arbitrary-oriented subspace clustering, it has evolved independently from different motivations. Here the motivation was to approximate nonlinearity. Here the motivation was in general to learn manifolds, which is also done by linearly approximating nonlinear manifold. And here correlation clustering, as you see, there's a plethora of different literature that we have, and they were originally developed to actually find clusters. So here the focus was on clustering by finding clusters that reside in subspaces, in low dimensional subspaces. And now you see here all these algorithms like ORCLUS, 4C, CoPark, HICO, ERIC, Cache, then SSCC, subspace correlation clustering, LUX, SONAR, ISAC, LM-class, or SC, and they may be many, many more which are not captured here. And you think, probably, do we really need to learn all of these algorithms? I mean, really go through every single of these algorithms, probably also these and these algorithms here. And the answer, of course, is no. This is not what we are aiming for, because it is of no use for you that you keep learning here of these 7 to 18, like the 11 different algorithms, that you learn them with every detail. This is of no use for you. But instead, what we're going to do, we look at a maximum handful of algorithms and ask, this is now the core message, what are the common and distinctive properties among the resulting clustering from different correlation clustering algorithms? So it's not about here's a second for loop and here's a case distinction and whatnot. We will look a bit into the algorithmic approach, but we will also ask, like, what are the differences? What can, for instance, 4C capture or detect what ORCLUS cannot, and vice versa? And we choose exemplary besides local PCA that we have already talked about. We will take a look at ORCLUS, 4C, and Cache, which is my personal favorite, to be honest. And after having a look at these three ones a bit more in detail, and contrasting what are the similarities and differences, then we try to figure out what are in general, independent of any of these algorithms, what are the high-level taxonomies, the differences by which you can investigate them, and decide which one to use when. Suppose you are going to be one of the leading heads, either in academia or in a company, and somebody approaches you and says, well, we've got high dimensional data and we want to cluster it, but there are too many features, we want to have fewer features, and we thought to use something like a correlation clustering method. I mean, the probability that somebody asks you exactly this is quite low, but anyway, suppose somebody asks you, okay, which of the algorithms should we choose? And there is no use for you to know every of these single algorithms that are presented here, but that you know, okay, so I can decide based on knowing, are we looking for local or global clusters? Are we relying on PCA, or do we wish to rely on PCA or on another technique? Do we want to have like dimensionality hierarchies, or do not we wish to capture dimensionality hierarchies? Do we want to have like certain dealings, handlings with noise or not? So these are different questions, and by knowing the differences, different distinctive or common properties, the taxonomies that after these three I will present you in detail after ORCLUS, 4C, and Cache, then I hope so. So this would be the goal. You can make decisions. So you can say, okay, so we know that there may be clusters that are not really dense, but they are described by the same line. So we may go for global correlation clustering. Okay, so that you have some aspects in your mind, and instead of blindly learning each of these algorithms. So of course, ORCLUS, 4C, and Cache are learned because they have some distinctive properties, but in general, yeah, It's more about the high level idea and the categories and taxonomies. So to approach that, we first need to revise, however, the general problem setting of clustering high dimensional data. So the problem setting is search for clusters in arbitrarily oriented subspaces of the original feature space. And the challenges are like twofold. So first we say find the relevant subspace. So we want to find these things here, the relevant ones of each relevant cluster. And the search space in this case is all possible arbitrarily oriented subspaces. So we can look for this one, this one, this one in rotation, also in translation. And the problem is in the axis parallel scenario. So the axis parallel subspace clustering, if you have like 3 axes, for instance, then you can say it's axis A and B, it's A and C, or it's B and C. So you have like an exponential number of potential subspaces you're looking for. In arbitrary oriented subspace clustering, things turn even worse. Why that? Because you have potentially an infinite number of potential subspaces in contrast to axis parallel subspace clustering, where it's only exponential. It's still terrible enough. So that's the reason why we have these heuristics, like the algorithms that Professor Kröger showed you, like click, subclue and such. But here it's infinite because you can say this is one rotation, then you can go a rotation which is off by 0.0001 degrees, or another by 0.000001, 0.000001, and so on and so forth. You can go infinitely. So you have infinite number of potential subspaces, not only for the rotation, also for the translation. So no. And the other way around, so we said we want to detect relevant subspace of each relevant cluster. We can say, well, we want to find the relevant cluster which resides in each relevant subspace. Here you may also rightfully ask, what is actually meant with relevant? Well, it depends. Since it is an unsupervised approach, you deem as relevant if things are, for instance, dense enough, like in Click, if the cells have minimum tau objects or something, or if you're a domain expert and say, this is relevant or this not. However, in this case, you also already have a bit of prior knowledge in influence. So here you have like relevant clusters, looking for relevant clusters and relevant subspaces. And the best partitioning of points, for instance, the minimum cut of the similarity graph, is known to be NP complete. So in both cases, we see it seems like a lost cause. And this is the reason why in correlation clustering, it's no exception to the rule. We also need to rely on heuristics. Just like local PCA is a heuristic and all the upcoming algorithms are heuristics. None of them is computing the one global exact and optimal result that one can have. Also, even the word optimality itself is almost philosophical, asking what is actually optimal in that sense, depending on the objective we specify. So we have even worse, this circular dependency here. Both challenges depend on each other. So in order to determine the correct, strike this correct out is a bad choice of words, to determine the relevant or suitable subspace of a cluster, we need to know at least some cluster members. On the other hand, in order to determine the meaningful or the relevant cluster memberships, we need to know the subspaces of all the clusters. So this is not really making a positive attitude. And the question is, how can we overcome the circular dependency problem, or at least mitigate the effect? And the idea is to integrate subspace search into the clustering process. And therefore, we need heuristics to solve, as mentioned before. And these heuristics have to solve or approach the subspace search problem and the clustering problem simultaneously. So in local PCA, we had this the projection distance that we had. So this projection distance is like one way for the subspace search, and at the same time for having a cluster assignment for saying this object belongs to this medoid or that object belongs to the other medoid simultaneously. What we need to keep in mind, if we found a relevant subspace, we may still have a big challenge to find the correct data set. So here the clusters that we have, yellow, red, green, and blue. Blue was the normal from this metabolite data set, and gray are the noise objects, are not separable in the correct subspace. So if we say this is like the one correct subspace, you project them here down, they are not separable here and here also not, as you remember. So this is, again, as a recap, this would be the clustering subspace, and this is like the correlation subspace. So what we rather need is a new cluster model. And a cluster here is a group of similar objects, but what is the concept of similarity that all members of the cluster share in this example? And that does not include any members from other clusters. And this asking for what is the concept of similarity that all these members share is almost a philosophical question, and something where we will get to it by approaching the algorithm, like, for instance, OCLUS. So here, as a recap, what we had so far, bottom-up approaches like subspace clustering, like click and subclue, which you know from previous lectures, then top-down approaches from projected clustering. So here we have each point is assigned to one subspace cluster or noise. There we had proclust or predicon. And correlation clustering in general is considered as a top-down approach. So each point is assigned to one subspace cluster or to noise. And there we are going to look at OCLUS for C and later on to cache. And here again, so just that you have this picture always in mind, we have cluster 3 exists in an axis parallel subspace, but cluster 1 and 2, they exist in arbitrary oriented subspaces. So if the cluster members are projected into the depicted subspace that we see here, the red one, the green one, and the blue one, the points are densely packed. So if we press these from cluster 2 down to this green line, they will be dense, they will be compact. The same for the red line and the same for the blue line. So subspace clustering and projected clustering algorithms find axis parallel subspaces as a take-home message. Correlation clustering is used for finding clusters that reside in arbitrarily oriented subspaces. So far up to this point, now stay tuned for the first, not the first, but the algorithm that we introduce after local PCA. It's called OCLUS after this video. Thank you for your attention so far. Take care and bye-bye.